Let's start with this route summarization. I think route summarization is pretty cool stuff. What it really depends upon is from what vantage point are we examining our IP networks? Our subnets are simply a range of addresses. So here 10.0.0.0/24 is a range of addresses from 10.0.0.0 through 10.0.0.255. If we look at subnets as simply ranges of addresses, we can use this to our advantage to help create some efficiency when we are creating static routes or configuring dynamic routing protocols. So here, the very first address in our range is always going to be our network address. The very last address in our range is always going to be the broadcast address. And then again, our mask is going to tell us which bits of the address are network portion and which bits are host portion. Well, if we examine a network here, we have these four networks, 10.0.0.0 through 10.0.3.0/24, attached to a router. And we add another router into the mix here and build a small network. Let's see what happens when we try to send a message with a destination IP address of 10.0.1.10. When that message arrives on the first router, which we're going to call router A, what it's going to do is it's going to do a route table lookup. Well, let's assume that on router A, we have 4 static routes configured, one for each one of our 4 networks connected to router B. What happens then is we do a route table lookup. The route table lookup is effectively going to treat each one of those subnets as a range of addresses, and it's going to find out which range of addresses match our destination address. So here, network 10.0.0.0 again is 10.0.0.0 through 10.0.0.255. 10.0.1.0 through 10.0.1.255, 10.0.2.0 through 10.0.2.255, and 10.0.3.0 through 10.0.3.255. Now this address of 10.0.1.10 matches the second network in our list here. So what we'll do then is we will use that static route and forward our message onto router B. When the message arrives on router B is going to have 4 directly connected networks, one for each one of these subnets. And here we're going to do the same lookup again. We're going to find out which one of these 4 directly connected networks contains the range of addresses where 10.0.1.10 exists, and then we'll use that route to forward our message to that network. Now let's take a look at a second example here, and this time let's forward our message to 10.0.3.99. When we get to router A, we of course have those 4 separate networks. Well, let's see if we can do something with those 4 separate networks to create fewer static routes on router A. So if we look at the ranges again here, and we start with the first network, if I add 1 to my broadcast address of my first network here, so 10.0.0.255 plus 1, what that's going to result in is the network address of our next range for this case. Here, 10.0.0.255 plus 1 equals 10.0.1.0, which is the network address of our next range of addresses here, which ends in 10.0.1.255. If we add 1 to that, we're going to get 10.0.2.0. The last address of that subnet is 10.0.2.255. If we add 1 to that, we get 10.0.3.0, and the last address in that range is 10.0.3.255. Well, what this means is that our 4 separate ranges of addresses here for our 4 subnets, what that equates to is one single range from 10.0.0.0 through 10.0.3.255. So we have a continuous range of addresses starting with the 0.0 and ending at 3.255. Well, what we can do is we can actually use this to our advantage. If I write out my network address, 10.0.0.0, and then right below it, I write down my broadcast address, what I can do then is I can compare the bits of these 2 addresses, and I can find where the similarities are and where the differences are. So what we'll notice here is the first 22 bits of this address are exactly the same in both cases. It's not till the 23rd bit where the values begin to change for each address. So if we look at this, the network address here is 10.0.0.0. The broadcast address, which has all 1s in the host portion, becomes 10.0.3.255. And that happens when we apply that subnet mask with 22 bits in the network portion and 10 bits in the host portion. What that translates to is 10.0.0.0 with a 22-bit mask, or 255.255.252.0. So we can say that these 4 subnets that I currently have configured as static routes on router A are equivalent to one subnet 10.0.0.0/22. So what I can do is I can actually create one static route on router A that will forward all the traffic correctly to all the networks connected to router B. So we'll add that now to our routing table. Now when we do that route table lookup, 10.0.399 is within the range of 10.0.0/22. So we use that route that we just configured to forward our message onto router B. When we get to router B now, router B is still going to have those 4 directly connected networks listed in its routing table. On router B, we can't summarize our 4 networks because they each are on a separate interface. So on router A, we can say that 10.0.0.0 through 10.0.3.255 all go to router B, but on router B, we have to have each separate network listed separately because they're directly connected. So now when it gets to router B, we're going to find the route that matches our destination address and forward our traffic out that interface. If we take this example a step further here, and we add some more networks to router B. So let's say connected to router B, we have those 10.0.0.0 through 10.0.3.0. And then we also add in 192.168.96.0/23 through 192.168.102.0/23, and then the 172.18 addresses there on the bottom. So we have 3 sets of networks directly connected to router B. Let's take a look at what static routes we can add to router A then to help minimize the size of router A's routing table. Right now we have that one route, 10.0.0.0/22, pointing to router B. Let's take a look at those 192.168 addresses now. So here what I want to do is I want to convert each one of these 4 network addresses to binary. We'll do that, and as we do that, we're going to just carry down that /23 mask so we can just observe what's happening as we write these out. So here we have 192.168.100.0/23, and then finally 192.168.102.0/23. Now we have those addresses written in binary. What I can do now is just start comparing the bits, just like I did in my first example. This time, though, I'm not writing out the broadcast addresses of each network. What I'm going to do here is simplify it a little bit, and we're just going to compare the bits in the network address for now. When I compare those bits, what I notice now is the first 21 bits of all 4 addresses are exactly the same. Because the first 21 bits are all the same, what I can do then is create a mask that has 21 bits in the network portion, allowing 11 bits in the host portion. What this will do now is this creates a subnet of 192.168.96.0/21, or 255.255.248.0. So 192.168.96.0/21 has a range starting with the 96.0 and ending with 103.255, which is the broadcast address for the 192.168.102.0/23 network. What we can do now is we can add that static route to router A and have it point to router B. So now instead of having 4 separate static routes, we can just do it as that one single static route with the /21 mask. Let's take a look at that last set of addresses here now. With our last set of addresses, we're going to do the same exact thing. We're going to convert each one of these sets of addresses to binary, using that /30-bit mask just as a guide as we write these down. If I then compare my bits, starting at the left, moving towards the right, what we're going to find out is that the first 27 bits are exactly the same, and the last 5 bits start to demonstrate differences. Well, this actually, though, creates a problem. In the other 2 examples, what we saw was that the very first address in our range, when we applied our summarized subnet mask, had all zeros in the host portion. Here, when I apply that subnet mask, in this case /27, my first address does not have all zeros in the host portion. Therefore, this is not the first address in my range. Additionally, if I look at the broadcast address for my very last network, what I'm going to find out with the /27 mask is that that last address in my range is not all ones. So I'm not starting with a network address with a /27 mask, and I'm not ending with a broadcast address with that /27 mask. What that's telling me is that my summarization is going to include more addresses than are listed in these 4 networks. If I do the calculation where I apply the /27 mask, and then I add all zeros in the host portion and all ones in the host portion to find my network address and broadcast address, what I find out is that my range of addresses goes from 172.18.75.160 through 172.18.75.191. Well, this is much larger than the range of addresses that I have listed in these 4 networks. Does this mean we can't do the summarization? No, we can absolutely do a summarization with a /27 mask. That is not a problem. The problem is that I might be creating a static route to more networks than I want to be creating. When we're doing route summarization, we can take advantage of the mathematics behind this and actually use this .160/27 network address here and apply it as a static route. But ideally, in my opinion, we want to be as specific as we possibly can to avoid errors in our network in the future when we're not expecting it. So I'm going to not use the /27 mask here, and we're going to analyze this a little bit differently so we can find a better way to summarize it. Well, just by examining the bits of my address here, if I separate these out into 2 separate summarizations, and I start with the top one, and I compare the bits of those 2 networks, what I find is that actually the first 29 bits of that address are identical in both cases. And then, if I calculate the broadcast address of 172.18.75.172/30, and I extend my /29 mask down, now what I see is I have all zeros in the host portion for my first address, all ones in the host portion for my last address. So now what I can do is then I can apply that mask of /29 to the 172.18.75.168 address. /29 allows me to summarize those 2 networks into one statement. If I then look at the bottom 2 networks, I can apply the same rules here. We find the matching bits, which are the first 29 bits. If I calculate that broadcast address for my second network and then apply my /29 mask, here again we'll find out that the first address in my range is all zeros in the host portion. The last address is all ones, which is the correct range from my network address to my broadcast address. So we can summarize that second set of addresses as 172.18.75.176/29. So here we can't do a perfect summarization of these 4 subnets into one network, but we can do 2 summarizations of these 4 networks to create a very specific route to each one of these 4 networks. So here now on router A, instead of adding 12 routes, one for each of the directly connected networks to router B, here I'm only adding 4 routes to get to each one of those networks.